Okay, for the next talk, I'm happy to announce Irene Valenzuela telling us about the structure of dualities and towers in Minkowski and AdS. Thank you.
Okay. Okay, so thank you very much. Thank you to the organizers for putting this together and the invitation to speak. So yeah, I'm going to talk about the structure of dualities and towers in Minkowski and AdS, which is based on work in collaboration with these people. And here, I'm just remarking the names and faces of the students and postdocs of the collaboration that are here, so you can talk to them. So Ignacio is my student, Jose is my postdoc. And yeah, so the plan is, okay, I want to talk about the structure of dualities. So I think dualities is one of the deepest things we've learned from string theory, right? That we divide the modular space in different regions that are better described by different descriptions. You can ask, okay, what are the possible descriptions one can get? How are they related to each other? What are the possible dualities? And these are very long, old-standing questions, very important. But recently, they are also, I think they are capturing a lot of attention because one way to tackle this question is precisely by classifying the possible towers of states that become light at infinite distance, as dictated by the distance conjecture. So just, for example, the simplest example, just to set the stage, you can have 10-dimensional type 2A, right? So you have one-dimensional modular space, just the dilaton. You can go to strong coupling, weak coupling, and then you have, all of you know, the tower of string oscillator modes becoming light at weak coupling, that indeed decays exponentially in terms of the geodesic distance. Or the tower of DC brain, so the Kaluza-Klein states from M theory becoming light at infinite distance. And this means that there are some scale at which quantum field theory breaks down, which is below the 10D Planck scale. Here's the string scale or the 11D Planck scale that give us information about the two duality frames. No? So here, the modular space gets divided in the two regions that are described by type 2A string theory or M theory on the circle. And just for later references, this string scale and this Planck scale is what we are calling all the time the species scale, okay? But it's not more than this. Okay, so what I want to do in this talk is I want to discuss some recent developments, understanding what are these possible duality frames, and especially how to combine them, okay? So I'm going to do this. I tell you what are the results, the state-of-the-art, both in Minkowski and AdS, so there is a bit for everyone, depending on your taste. And in Minkowski, of course, there has been many, many works identifying all these tower of states. You've already heard about some of them. In this talk, we are gonna, rather than focusing on what happens in each limit, we are trying to understand how you can combine the different limits, okay? So how you paste all these duality frames. And then for AdS, much less is known. So we are trying to understand what are the possible towers, no, that appear in these infinite distance limits in AdS. And starting, I'm going to give you some results, starting in some sort of classification of this using the dual CFT, which will bring us to see new corners that we have what we think are non-critical strings, tensionless strings. And then, well, I have a bonus slide, depending on the time, to see how, thinking how to paste these limits, how to combine these limits together, give you a new argument for no-scale separation in AdS. Okay, so let's start with Minkowski, first part of the talk, compactifications to flat space. So I want to understand what is the structure of the possible towers and how this can help us to understand how to combine the different duality frames and the different dualities. No? What are the possible dualities we have? So let's consider some geodesic that approaches some infinite distance boundary, so that at a given point, this is the tangent vector of the geodesic trajectory. And then we're going to have tower of states that become light. So remember, the mass of these towers, it's a function of the moduli. So at a given point, you can compute what is the variation, what is this gradient of the mass. And these quantities are going to be the protagonist of the talk. So this is what we call this tower vector and species vector that give us information about the variation of the masses in the modular space. So for example, if we have this tower of states that decay exponentially, the exponential rate, which, I mean, the value of the exponential rate is one of the main open questions on the distance, is just the projection, right, of this vector over the corresponding trajectory. Okay, so the first observation is that the microscopic nature of the tower gives you information about what is the modulus of this vector. Okay, so from all the works we've been studying, classifying what are the possible towers, it seems that there is always some frame in which they look as Kaluza-Klein states or towers of oscillator modes for the critical string. So this is what is encoded in the emergent string conjecture that we already heard about. Now, if this is the case, then this is fixing, right, the value of this modulus just in terms of the number of dimensions of the space-time, this D. And for instance, in the case of KK, let me not consider warping for the moment, just in terms of the number of extra dimensions that you decompactify. Very good. Now, the message is that the microscopic nature of the tower does much more than fixing only this modulus. It's also going to fix the product between the vectors, okay? So what we do is that if you assume the emergent string conjecture, so that everything you have are Kaluza-Klein towers or string towers, then in this ongoing work that we hope to put in archive either this week or next week, we derive a set of taxonomic rules that must be satisfied for every regular infinite distance limit in any compactification. And I will tell you in a moment what does it mean regular. Okay? So as you can see here, in particular, it's not only the lengths of the vectors, but also like the angles between them when you have several towers are constrained, okay, and are fixed. Now, two comments here. One, here we are including this pattern that we observed in this previous paper with Alberto Castellano and Ignacio Ruiz. Okay, so this gives a relation between the leading tower and the species scale, which is nothing but either some string scale or some Planck scale, whatever is lighter, okay, so whatever you find first, in a sense. So we found this pattern from top down, like from string compactifications. Like we basically tried to analyze as many setups as we could, both from 32 to only 4 supercharges, like including Calabi-Yau compactifications, everything. And it was very amazing how, I don't know, when you study all these limits, there's a rich structure of limits, different combination of the towers. You can have beautiful classifications related to beautiful mathematical theorems. And then you check this behavior, this dot product, and in all these cases and all these limits and all these compactifications, it gives you this universal result that only depends on the dimension of the space-time. So it's completely insensitive to what compactification you started with and what was the tower. So it's even embarrassing how simple it is. And I believe that there might be a way to derive it purely from bottom up, like thinking of black holes and so on, because in the end, this is giving you a constraint on the growth of the density of the states that you may have. But okay, this might be for the future. What we do here is that we want to clarify that, yeah, this pattern and especially these other rules with the dot product of the towers, yes, you can derive it from bottom up if you assume two things. One is the emergent string conjecture recursively. So that means that that's very important. It means that you impose it in every step of the decompactification whenever you have several towers. And that's important because it implies some conditions on the existence of bound states that we already discussed here. And then you can derive it if you have a regular infinite distance limit. So what does it mean regular? Regular means that the leading tower is not degenerate, so there are no several towers decaying at the same rate. Okay? And if there is if it's a decompactification, it decompactifies to an asymptotically empty Ricci flat. So that if you have some warping or non-trivial profile, this warping gets diluted in the limit, so you decompactify to a Minkowski vacuum. Okay? Now, these conditions are sufficient, not necessary, in the sense that you can, for example, violate the first one, and still these rules, you can see certain cases apply, especially this one we checked a lot in the previous paper. The second condition is more tricky. And actually, if you decompactify to some running solution that is not a vacuum, we know that, for example, this first rule gets violated. Okay, so this needs to be modified. Now, the interesting thing is that we argue that regular limits are generic in the sense that this, when you violate this happens only for trajectories of measure 0, in the sense that you can kind of divide the modular space into different regions with families of continuous families of limits, and if you move a bit away from an irregular limit, it becomes regular, so that it only matters when you try to glue the different regions with each other and try to understand how to glue the different building blocks. Okay, that is irregularity matters. Okay, so what are then? So the point is that you can use this to construct some building blocks, and then you have to learn and to study how to combine. So what are these building blocks? So the point is that these towers, since we know the dot product, this fixes the geometry. So the tower generates some simplex, which we call the frame simplex, to which the species scale is orthogonal. And here I just put two examples based on having the species scale being a string scale or a Planck scale. Okay? And you can study very nicely the geometry associated with these vectors. And the point is that, I mean, you construct this for each infinite distance limit, right? So remember, for each limit, you compute in the tangent plane what are these vectors and what is the geometry they span. But if you now consider different infinite distance limit, as long as you don't break this conditional regularity and you stay within this cone, the geometry is rigid, okay? Doesn't change. So you can associate one of these frame simplex to each duality frame. Okay, so to each region in which inside you have all regular limits. Okay, so these are our building blocks. And now you can see where I'm going. In certain cases, you can then go a step further and try to see, okay, now I have these building blocks. How can I glue them together to fill the full modular space? And in certain cases, I mean, one has to study this in more detail. In this paper, we take the first step, in which we assume that you have like asymptotically flat slices and so on, so you can just simply glue them to form a full polytope. Okay? So this is an example in 2 dimensions, in which you are gluing different, like these simplexes that are the convex hull of the vectors. And this is another example in 3 dimensions. So that for this, for example, our favorite star of M theory, right, in which we have the modular space divided in the different duality frames, this translates to this polytope, which is just this triangle. And then the towers separate the different duality frames. Right? So you can associate one to each of them, and then you can start playing and say, okay, what are the possible polytopes I can have? Just assuming the emergent string conjecture, right? So completing the full polytope is not trivial because, I mean, you need, for instance, in 2D, you need that all the sum of the angles to add to pi, right? So there are only like a finite number of combinations you can make. And this is just one example in which one classifies possible 2D polytopes with a maximum dimension of the compactification. And you can already here in this simple example, one can see that many of them we actually know how they arise from string theory. So as I said, this is the typical one from M theory and the torus. But others are new. So one could then wonder, like these are in red are new, so maybe there is something wrong with them, and maybe they are in the Swampland, or maybe they are like other corners or new corners of the landscape. And just one last comment, here you can see these balls, these gray balls. This is just to illustrate that these polytopes, but in general, all of them that you can construct following these rules, includes, the convex hull includes this ball of radius 1 over square root of d minus 2, meaning that it satisfies this convex hull version of the distance conjecture, where the minimum value is set to the proposed lower bound of the sharpened distance conjecture. Okay? Meaning that if you move in a direction in these planes, there is always a tower that decays exponentially, at least with this exponential rate. Okay? Good. So there are more things that you can do here. You can do a similar study for species scales and so on. But let me now move to the second part, which is how all this story changes in AdS. Okay? So it's very nice. We have learned about, we are learning a lot about Minkowski and reproducing, many of these dualities and so on. So if I am now in AdS background, what do I have? Do I still have always Kaluza-Klein towers and string towers? Can I get something new? What's going on? So let's consider now that we have an AdS vacuum in which you still have some moduli space, so there are some flat directions. Okay? These flat directions, this moduli space, maps to the conformal manifold on the CFT, which is the space of exactly marginal couplings. The field metric that we use to measure distances maps to the Samolov-Hikov metric, which is the two-point function of the marginal correlators and operators. And having this tower of states becoming massless, right, that are light, is going to map to having tower of operators that are close to saturating the unitarity bound. So the distance conjecture implies that there should be an infinite tower of operators saturating the unitarity bound at every infinite distance limit measured by the Samolov-Hikov metric, such that the anomalous dimension decays exponentially in terms of this distance. Okay? Okay, so does this happen? Well, if you now study from the CFT perspective, all known examples satisfy this. I will explain how. But of course, it's interesting to translate it to the CFT language, because then also give you a new handle to actually try to prove this statement, not just based on examples, but really try to see what is, whether we can just use CFT techniques to prove the existence of these towers. And with this, there has been actually recent progress already this direction, so that when you have the infinite tower, you're going to have the infinite distance, has been recently proven by Jose and Florent for higher spin gap, like for higher dimensions, or Hiroshi and Jifan recently in 2 dimensions. And then the other direction is not proven yet. I think it might be a matter of time so that we could have a proof of the distance conjecture on CFTs. But at the moment, at least it's supported by all the known examples. Okay? So what is the nature of the tower? So here I'm going to, the goal was to understand what are the possible dualities, and what are the possible natures of the tower. So what is the nature of the tower in this case? Here is very different if you are in 2 dimensions. So this is the dimension of the CFT, okay? Or in higher dimensions. So in 2 dimensions, it seems it's always about scalar operator, like the scalar gap goes to 0. In higher dimensions, it's about higher spin fields. The higher spin gap goes to 0 at infinite distance, okay? So what I want to do in the rest of the talk is to focus on the second case, okay? So in the higher dimensions, so the bulk is at least 4 dimensions. And tell you a bit, what are these tower of high spin modes and what are the possibilities that we have, okay? So let's focus on higher dimensions, and for that, we are going to focus on 4-dimensional superconformal field theories, just because these are the only known examples that have non-compact conformal manifolds. So, our goal is try to see, okay, what are the possibilities that arise on CFT? So let's look at the examples that are known. So if we focus on these 4-dimensional superconformal field theories with any level of supersymmetry, all the known infinite distance limits are weak coupling points, which means that from the CFT perspective, there is a gauge coupling that goes to 0. Okay, so that there is going to be a sector of the CFT that gets free. Okay, at least a subsector becomes free. And that's why we get the tower of higher spin modes, because by the paper of Maldacena and Sivoedov, we know that any 3 point has a higher spin symmetry and vice versa. So that's why you have this tower of higher spin fields at these infinite distance limits. Now, I don't have a lot of time to explain the details. This is something we did in this paper also with Comron. One can prove that for these weak coupling points, indeed one has the higher spin tower decaying exponentially. So one can compute the metric explicitly in general for all these points and compute what is the exponential rate of this tower of higher spin modes. So the result is that there is a tower that decays with this exponential rate, which is given by the ratio of the central charge over the dimension of the gauge group that gets free. Okay? Now, 2 things. First thing one can notice is that this exponential rate is lower bounded. So again, there is a minimum value that one can take. But not only that, if you check more carefully the CFT, one realizes that this value is not random, like cannot take any value. It's actually very constrained. So we want to classify what are the possible values that you can have. And as a first step, what we are going to do, we will do in this paper with Jose, is that we focus on CFTs that have a simple gauge factor so that everything gets free. So this is like having only one modulus. Okay, so it's the first step, like you first classify one modulus, and then you will start trying to combine and group pieces together. So when you have only one factor, and this, the possible Lagrangian CFTs that you have are classified, they are beautiful tables with all the possibilities. You can compute this value of the exponential rate, and from all these examples, one gets only 3 values of the exponential rate. Okay? So what does this mean? Okay, what do these 3 values correspond? So this is something we noticed in this paper, but now we're trying to understand, okay, what can we say about these values, no? Like what distinguishes them, these 3 limits. So first thing we notice is that the 3 values appear because you can actually write this exponential rate in this case as a function of the ratio of the 2 central charges of the CFT, A over C. And for all these 4 superconformal field theories, actually there are only 3 values of the ratio that appear, and that gives rise to these 3 values of the exponential rate. Okay? So these are large N CFTs, so we have a weakly coupled AdS, but not necessarily a large cup. Okay? We are only requiring to have a large N. Okay, so very good, but what does it mean this from the perspective of the bulk, no? Of what is the microscopic nature of the tower? Well, all these cases are going to correspond, they are higher spin fields, so they are going to correspond in the bulk to some sort of tensionless string limit, okay? But we have 3 different values, and I told you at the very beginning that the nature of the tower was fixing this value of the exponential rate, so does this mean that we have 3 types of strings, like 3 types of tensionless strings? Well, we think that the answer is yes. That's what we are exploring in this paper, because, for instance, we can compute the thermal partition function on S3 to count like what is the density of states, like how many states we have in the free limit, and study what is the Hagedorn behavior. Okay, so we see that indeed there is a Hagedorn behavior, so we have like sort of a tensionless string. But the density of states is different for the 3 cases. In particular, the Hagedorn temperature, okay, that fixes this density of the states, is different, and we are working on giving a final formula for this Hagedorn temperature just in terms of this ratio of the central charges of the A over C, which means that it's just a function of this exponential rate. So that for each of these exponential rates, there is a different value of the Hagedorn temperature. So the first one, indeed, is when A is equal C. So it corresponds to all Einstein gravity theories. So whenever you have an Einstein gravity in the bulk, you get the same value of the exponential rate, which matches with the critical string. And then like the mergent string conjecture is satisfied, because in all these Einstein gravity theories, you have just the higher spin modes just come from the critical string, and that's it. But if you go to non-Einstein theories, the distance conjecture still works, but then you get other types of higher spin modes, other types of strings that we call non-critical strings just because the density of states is different. Okay? So it would be very interesting to understand more the physics of these other non-critical strings, so like other corners of the landscape. Okay, so with this I finished. I had like a bonus slide, so let me not go into the details because I think I'm running out of time probably. So just quickly tell you what it was about, and then you can ask me later. The point is that here you can say, okay, fine, you discuss this for each like one individual limit. What happens if you start combining limits? And as a first step, you can take, for example, just n equals 4 super means, but consider the full field space in the sense that I don't consider only the higher spin fields and in the conformal manifold, but also the Kaluza-Klein modes that become light when the volume becomes large. Okay, so this is going beyond the conformal manifold, but still you can compute like the vectors for the Kaluza-Klein tower, the string tower, and so on. For the strings, you really need to use the CFT result when you go to the regime in which the volume is small in string units. But okay, we have now all the data, so you can still plot these vectors as I did in the first part of the talk. And surprisingly, it still satisfies all these taxonomic rules, where now you can still think of it like having like two frame simplices that you glue together through the holographic duality. And you have on one region, on one side the supergravity regime, the other side the field theory regime. And moreover, they also include this ball of radius 1 over square root of d minus 2, so they also satisfy this sharpened distance conjecture. But they do that marginally in the sense that this is working just because there is no scale separation. If you allow, and if you imagine that you have this AdS 5 crosses 5, but with some scale separation of this 5 with respect to the AdS scale, then this wouldn't be this beautiful straight line. It would actually cut the ball. So just from the normal distance conjecture, having this sharpened lower value for the exponential rate, you can see that whenever you have this conformal manifold and these higher spin points in Einstein gravity theories, you cannot have scale separation if you satisfy this bound. So that was it, and let me just stop here, and thank you for your attention.